Okay, chapter 7, we're looking at alkenes and alkynes. We'll be looking at ways, some reactions to make an alkene and to make an alkyne. Before we get to the reactions, though, we got just a little bit of nomenclature to cover. And this is in section 2. Section 1 is just kind of an introduction, telling you what's coming up in the chapter. If you recall from previous things on alkenes, we can have cis alkenes and we can have trans alkenes. So a cis alkene is where we have two substituents coming off the double bond and they are on the same side. And trans is where we have two substituents coming off and they're on opposite sides of the double bond. But what do we do if there's more than two substituents? I can't use cis and trans. Maybe something like this. Here I've got three things coming off that double bond. You got a hydrogen and three substituents coming off. Can't use cis and trans. But there is still, this does still have a diastereomer that's possible. Cis and trans are diastereomers. And this also has a diastereomer, but we can't call them cis and trans. Here is the diastereomer. Those two are diastereomers of one another. So how do I tell the difference between the two? They are different molecules, and I need some way to differentiate between them. What we're going to do is we're going to assign priorities to the two substituents, to the two groups that are on each carbon of the double bond. So you're going to do one carbon at a time. Let's go to the first carbon here. And we're going to, I'm going to highlight that in red. We're going to assign priorities to the two things that are coming off of that carbon. And we do that in the same way as we did R and S back earlier. We assign priorities to figure out R and S. So here I have a bromo group and a carbon. Bromine and carbon. Higher atomic number gets the higher priority. So bromine has a higher atomic number, it's number 35 there on the periodic table. Carbon is number 6. So bromine gets the top priority, carbon gets the second priority. We're going to do the exact same thing on the other carbon of the double bond. We'll assign priorities on that one for the two things that are coming off. Here I have a fluorine and I have hydrogen. Fluorine, higher atomic number, it gets the higher priority. And the hydrogen would be the second priority. And you can see that we have the same type thing going on here with the other one. I'll just go ahead and put it on here. But you can see the difference in the two. Here in the first one, the two top priorities are on the same side of the double bond, and here the two top priorities are on the opposite sides of the double bond. Now I can't use cis and trans because cis and trans are only for di-substituted alkenes. I got two substituents on there. So I need something different. We use the letters E and Z. One of these is going to get the E assignment and one's going to get the Z assignment. Now for some reason students have trouble with E and Z. Students usually have no trouble with cis and trans, but they have trouble remembering which is the E and which is the Z. So I'm going to give you something stupid so that you'll never forget this. Little stupid thing stick in your head. Which one gets the Z assignment? If your top priorities are on the same side, instead of same side, told you it's stupid, but you'll never forget it. you'll always remember, 10 years from now, you'll still remember same side. It's that stupid. If the two top priorities are on the same side, it's Z. If they're on opposite sides, then we know we get the other one, the E. Now those letters would just go out in the front, just like cis and trans goes out in the front when we write out a name for the compound. So no difference there. You just stick it out in the front of your name. Let's try another. Let's do another one here, and you can tell me whether it's the Z or the E assignment. Looking at this example, we got 4 substituents on here. Is this an E or a Z? Assign your priorities on each carbon of the double bond. What?
Z.
I hear Z. I hear anything else? Let's see what we got here. Go to the first carbon of the double bond. Assign priorities. The iodine and the bromine. Iodine's number 53 arrow on the periodic table, atomic number 53, bromine's number 35. Iodine is the top priority, the bromo group is the second priority. If you go to the other carbon of the double bond, assign priorities. Carbon, it's a tie. You have to go out further to break the tie. You go out further, this one's got hydrogens on it. You go out further, this one's got a carbon on it. Carbon beats the hydrogen. So this is top priority, this is second priority. Our top priorities are on opposite sides. This gets the E assignment. Okay, we didn't do very well on that one. Let's try another one. Okay, looking at that one. Is that an E or a Z? Anybody?
Z.
Z. Okay, let's take a look. Got a 50-50 chance. Let's assign priorities on each carbon of the double bond. So I'm going to do the top one up here. You got hydrogen versus a carbon. Carbon's a higher priority than the hydrogen. So this is top priority. This is second priority. We do the same thing on the other carbon of the double bond. Looking at what's coming off of it is carbon versus carbon. It's a tie, so you have to go out further. This one's got an oxygen on it. This one's double bonded to an oxygen. Now, if you recall, when we have double bonds, triple bonds, we pretend that each one of those bonds is to a separate atom. So this double bond to the oxygen, we pretend that that's separate bonds to two separate oxygens. So this carbon's got one oxygen, this has got two oxygens beat the one oxygen. So this is the top priority, this is the second priority. So let me just put my double bond back there. So we have the two top priorities are on the same side. This is the Z assignment. About this one. Anybody got an answer for me? Z? Anybody have a different answer? What? Both? We can't have both. You can have either E or Z or none of the above. Does this have a diastereomer? Can you assign priorities there? Look, let's take a look. First carbon, fluorine, fluorine. Which one's higher priority? They're the same. I can't do priorities. This does not have a diastereomer because these are the same group here. There is no diastereomer possible for this. See, your diastereomer is where you switch two of these. If I switch the fluorines, it's still the same molecule. There is no diastereomer, therefore no E or Z. This has got the same thing on the same carbon there. Two fluorines on the same carbon. There is no E or Z. I can't assign priorities to those two. So that was a trick just to see if you're paying attention. Okay, any questions on our E or Z assignments? We're going to move on now to stability of alkenes. And this is going to help us in some of the reactions that we will look at later. I'm going to put up two generic alkenes here. Looking at these two alkenes, we'll put up more here in a moment, but let's just start with two of them here. And I'm doing generic with some R groups out here. The first one has got 4 R groups there. We call this a tetrasubstituted alkene. The other one is tri-substituted. It's got 3 R groups and a hydrogen. So 3 R groups is tri-substituted. Looking at those two, using just common sense, which do you think would be the more stable alkene? Which would be the least reactive? If something wants to come in and react with that double bond, which one do you think it would be the least reactive? Which one is better protected? The tetrasubstituted. Tetrasubstituted is going to be more stable than the tri-substituted. Think about this. This has got 4 big old groups around that double bond that's helping protect it. The other one has got 3 big old groups, but one is a tiny hydrogen. So if something wants to come in and react with that double bond, it can come in on this side. It's blocked on the other side, but we have one side there that's pretty open. So the tetrasubstitute is always going to be more stable than a tri-substituted. Tri-substituted is always going to be more stable than a di-substituted. Now with the di-substituted, we have some different di-substituted. Here is the trans di-substituted. You can also have a cis di-substituted, of course. And of those two, of those two, trans is always more stable than the cis. We've got the same amount of protection around the double bond. You have two R groups in both of them. You got the same amount of protection, but the problem with the cis is having those two R groups on the same side, there could be some sterics in between here, where those groups are bumping into one another. So it's better to have them on opposite sides, so the trans is always more stable than the cis. Now, di-substituted, I've run out of room, I'm going to have to go to here to the bottom. Di-substituted is always more stable than a mono-substituted. So we only have the one substituent and we got three hydrogens. And monosubstituted is going to be more stable than an unsubstituted. We got no substituent. It's all hydrogens. So that's our order here for the stability of our alkenes. Questions on that so far? So this is going to direct some of our reactions as to what product we're going to get later when we start making some alkenes. It makes sense that if you have a choice between forming two different alkenes, we would want to make the more substituted one because it's more stable. And we'll see that in some of our reactions later. Now, let's look at some other things with stability. So substitution is the most important part of the stability of alkenes. But if substitution is the same, a cyclic alkene is more stable than an acyclic. So if I were to compare these two molecules, looking at these two molecules, this first one here is a tri-substituted. Looking at the carbons of the double bond, let's just see that it's tri-substituted. So, of my two carbons here of the double bond, here is a substituent. I'll put an R there. You got a CH2 on this side. Here you got an R, you got a CH3. Down here on the other carbon of the double bond, we have a CH2 on this side. That's our R group. And then on this side, not shown, there was a hydrogen. So that's not a substituent. This has got three R groups, three substituents. That's a tri-substitute. If you go to the other one is also tri-substitute. So if the substitution is the same, then the more stable one is the one where the double bond is in the ring. The one in the ring, where the double bond's in the ring, is more stable. A cyclic alkene is more stable than an acyclic. Only if the substitution is the same. If I were to compare this one with this molecule, see, this alkene is only di-substituted. Tri-substituted always beats the di-substituted. But if our substitution is the same, then you're more stable to have the double bond in the ring. Substitution is the most important. Tri-substituted always beats a di-substituted. Doesn't matter whether it's in a ring or not. Now let's go back to the first two here and think about this a little bit. Why is it more stable to have the double bond in the ring than not in a ring? Well, if something wants to come in and react with that double bond, yes, they both have three groups around it protecting it and the one little tiny hydrogen. So my eraser, let's say it wants to react with the double bond. Pretty easy to get it on this side. But it could even possibly maybe squeeze in, maybe it turns sideways or something, it squeezes in between the two methyl groups. But over here, got the three R groups and the little tiny hydrogen. Yes, no trouble getting in on this side, but if you look, get between the two R groups like I did up here between the two methyl groups, it could squeeze in there. Here, you got the ring in the way. It can't even squeeze in between there. So that ring provides a little bit more protection. So again, substitution part's the most important. Tri-substituted always beats the di-substituted, but if you have a tie, you're more stable in the ring. Questions on that? Okay, we're going to skip a couple sections here. We're going to skip section 4. Section 4, all it's stating is that it's looking at cyclic alkenes, and all it says is that when you have a double bond in a ring, all of these are always cis. It's always a cis double bond in a ring. You can't have a trans double bond in a ring. It's too twisted. That's all that section is saying. So we'll just skip it. It doesn't have any information in it. We're also going to skip section 5. And that gets us to some reactions now. We are going to look at elimination reactions. Of alkyl halides. A name that's often used when we do an elimination reaction of an alkyl halide, these are often called dehydrohalogenation. D means you're removing something. We're removing a hydrogen. The hydro is for a hydrogen and a halogen atom. So it's called a dehydrohalogenation. We're removing a hydrogen atom and a halogen atom. Removing an HX out of the molecule. These are also called, and you'll see why, these are also called beta eliminations. So a dehydrohalogenation reaction, or often called a beta elimination. Let's look at a generic example here to start with, and then we'll go through specific examples. And I'm just going to put some lines out here, some bonds to something. I'm not showing what else is out here. So here we have an alkyl halide. And we're going to react that with a base. And we'll talk about what bases are required here in a moment. The base is going to remove a beta hydrogen. That's where we get the beta elimination name from. The alpha carbon is the carbon with the halogen, with our leaving group. That's the alpha carbon. The next carbon out would be a beta carbon. This is a beta carbon. Alpha is where your halogen atom is, or leaving group is. Next carbon over is beta. The hydrogen that's on a beta carbon is called a beta hydrogen. our base is going to come and grab a beta hydrogen. And let's take a look as to why it wants to do that. If we grab the beta hydrogen, so we're going to form a bond between the base and that hydrogen atom. The electrons between the hydrogen and the carbon here, those two electrons in that bond, they're going to kick toward the alpha carbon to form a double bond, and that pushes the leaving group off. So that our product here is we make an alkene. The base grabbed the hydrogen, so you got a bond between the hydrogen and whatever the base was, and we kicked off the halogen, so there's an X minus out there somewhere, but we've made an alkene. Let's talk about the bases that are required to do this reaction. Not all bases will work. Not all alkyl halides will work. So we're going to discuss these. Let's talk about the bases. The bases that are used, we must have strong bases. You need strong bases. Now, what is a strong base? Now, last class period I gave you a list of some strong bases, but we'll review that. So I gave you a chart to tell you which way these reactions are going to go, if they're going to do SN2, SN1, E2, E1. But also with that, I gave you a list of some strong bases. So let's review those. Some strong bases include a hydroxide, doesn't matter which hydroxide, could be sodium hydroxide, potassium hydroxide, lithium hydroxide. That doesn't matter. Just a hydroxide. The metal doesn't matter. We said an alkoxide was a strong base. It's where you have a full negative charge on the oxygen. So it's the same as like the hydroxide. Just we got an R group out there instead of a hydrogen. Doesn't matter what the R group is. It could be a methyl group, ethyl group, propyl group, butyl group. Doesn't matter. So this could be things like sodium methoxide. Strong base. Full plus charge on the sodium, full negative charge on that oxygen. Sodium doesn't matter. It's the methoxide that is the base. We could have potassium ethoxide. Full plus charge on the metal, full negative charge on that oxygen. Doesn't matter about the metal. That ethoxide is our base. That's a strong base. Okay, so any of the alkoxides are strong bases. Another strong base that we talked about last time was the hydride. Hydride's an H minus. Doesn't matter what the metal is. This could be sodium hydride, lithium hydride, potassium hydride. Does not matter. It's a hydride, H minus. Those are very strong bases. And then finally we talked about the full negative charge on a nitrogen. This is confusing. This is called an amide, even though we're used to an amide being a nitrogen connected to a carbonyl. This is still called an amide. I don't know why they don't have a different name. So doesn't matter what the counter ion is. This could be sodium amide, potassium amide, doesn't matter, lithium. There's a full plus charge on the sodium there, full negative charge on the nitrogen. That's a strong base. We don't have to have hydrogen on the nitrogen. We could have other things. So this could be, say, 2 methyl groups. That would still be, as long as there's a full negative charge on the nitrogen, that is a strong base. Is this a strong base? No. This is neutral. Ammonia is a weak base. You need a full negative charge to be a strong base there. That one's weak. So I always get students that get this confused. NH3 and an NH2. NH2's got a full negative charge. NH3 is neutral. That's a weak base. So that's not on our list. I'm going to erase that off real quick. Okay. These are our strong bases. There are other strong bases out there, but I'm going to stick to these 4 groups here at the moment. We'll learn more later, but this is enough. We got so much to try to remember right now. This is plenty to try to remember. Let's examine our mechanism in a little bit more detail. I showed you the mechanism, the curved arrows there a moment ago. But let's look at a specific example. And we'll talk a little bit more about it. Let me draw the hydrogen sticking out so we can see them. Now, let's examine what we have, and then we'll go through our mechanism. If you look at the alkyl halide, our alkyl halide, this is a secondary alkyl halide. If you recall the chart that I gave you last time, secondary alkyl halides, if you look at that chart, secondary alkyl halides do SN2 with weak bases. They do an E2 with a strong base. This is a strong base. So this is going to do an E2 reaction. Now, E2. We haven't seen the name E2 yet. E2. What is E2? By the way, this is section 7. I forgot to write that up there. Section 7 is looking at E2 reaction. E stands for elimination. And the 2 stands for bimolecular, just like the SN2. The 2 stood for bimolecular there as well. So an E2 is a bimolecular elimination reaction. Let's look at our mechanism. We said before that we're doing a beta elimination. Alpha is the carbon with the leaving group. Alpha is the one here with the bromine. That's our leaving group. The next carbon out is beta. I have beta here and I have a beta here. Now in this example, the 2 beta positions are identical. They're both methyl groups. So it doesn't matter which one we go to. If they're not the same, then it is going to matter, and we'll talk about that next. But my first example, they're the same, so it does not matter which beta position you go to. The base is going to come and grab a beta hydrogen. That's our mechanism. This is the mechanism for the E2 reaction, also called the dehydrohalogenation, also called a beta elimination reaction. All this is referring to the same thing. We grab a beta hydrogen. The electrons in that carbon-hydrogen bond kick toward the alpha carbon to form a double bond, and that pushes off our leaving group. Our product here, we get the alkene. There's our alkene product. NH2 minus or base grab the hydrogen, so as a byproduct we'd have NH3. We kick the bromine off, so we've got a bromine anion. Sodium, spectator, it balances the charge out, so there's our byproducts. But we've made an alkene. Let's look at the kinetics of the reaction. Kinetics is talking about the rates of the reaction. Now I've got the full mechanism here on the board. If you recall, the rate of any reaction equals the rate constant of the slowest step. Well, if you look, we only have one step. Everything happens in one step. All of this happens at exactly the same time. The base grabs the beta hydrogen at the same time the electrons kick in to form the double bond. At the same time our leaving group leaves. That all happens at exactly the same time. I only have the one step. So the rate equals the rate constant of our slowest step. Well, there's only one step. Well, there's a rate constant there for that step. Times the concentration of the species that are involved in that slowest step. So I'll let you tell me what's involved here. Alkyl halide. Anything else? The base. Anything else? Nope. That's all that's got arrows on it. You're looking at your mechanism, look where the arrows are, the curved arrows. That's what's involved. Base is involved, it comes and grabs the hydrogen, and the alkyl halide's involved. It's losing the hydrogen and losing the bromine. There's our rate equation for this reaction. So you can see where they get the 2. The rate depends on the concentration of 2 species. It's a bimolecular reaction. Now if you look back in your notes, this is the same rate equation that we saw for SN2. Now SN2, I wrote the word nucleophile here instead of base, but a base and a nucleophile is the same thing. A base is a nucleophile and a nucleophile is a base. So they have the exact same rate equation. They're always competing with one another. SN2 and E2 are always competing with one another. Now what I gave you in that chart the other day is the one that wins. They're always competing, but I've given you in that chart the one that wins out under the conditions that I had listed there. So, for a secondary alkyl halide with a strong base, the E2 wins out, and we get our elimination. If I were to have a weak base here, then SN2 wins out, and we get substitution. But they're always competing with one another. So with these reactions, you're never going to get 100% yield. So don't freak out in the lab when you don't get 100% yield, because we often have competing reactions. I don't know what the yield is on this one here, but we probably get, I don't know, maybe 90% of this alkene, and the other 10% may be an SN2 substitution product. The E2 is the major product, but you still get a little bit of SN2. So these reactions are always competing. Now on the exam, your next exam, or any of my exams, I only ask for the major product. This is the major product. You'll have some substitution that's a minor product. I said maybe 10%. But this is the major product, and that's all we're concerned about. Now, with this one, this example, we didn't have a choice. I had 2 beta positions, but there was no option. You get the same alkene no matter which one you go to, because it's methyl and methyl. Both beta positions are the same. What if they weren't the same? What if they were different? we're next going to look at Zaits Rule. And before I write it up, I don't think we need the rule. I hate rules. There's always exceptions to every rule and things like that. So I hate rules. What there's never an exception to is we almost always want to form the more stable product. That's the driving force of things. You always want to make something that's more stable. So let's take a look at an example here. And I'm just going to react with the same base that I had here a moment ago. So if you examine our reaction, we have a secondary alkyl halide. We have strong base. Secondary alkyl halide with a strong base will do an E2 elimination. So we know we're going to get an alkene as our product. Now, the problem with this one, go to your alpha position. There's alpha, carbon with the halide, with our leaving group. Next one out is beta. So next carbon out is beta. Got a beta here, and I have a beta here. And these are not the same this time. These are different. The green one, you can see that's a methyl group, and the other beta, that's a CH2 group. Those are different. They're going to give different products. My base could come and grab the green beta hydrogen. Electrons kick out of the carbon-hydrogen bond. Those electrons kick toward the alpha carbon to form a double bond and kick our halogen off. And this is the alkene that we would get. There's the alkene that you would get if you grab that beta hydrogen. If we go to the other beta position, the base could grab this beta hydrogen. Electrons kick toward the alpha position to form the double bond and kick the leaving group off. Then this is the alkene that we would get. We'll get some of both. You'll get some of both. But one of them is the major. You'll get a lot more of one than you do the other. Which of those two do you think we would get more of? The one there in the blue or the one there in the green?
Green.
I hear green. Does anybody else have a different answer? Anybody want to say blue? Okay, we've got some blue. So, why, whichever color you chose there, why did you go with your reason? Why would we get more of the blue or more of the green? What did I say there a moment ago? Most reactions, before I put up Zaits Rule, we can use his rule and it'll tell us, but most reactions, you want to form the more stable product. Which of those two is more stable? The blue one. This one is a di-substituted alkene. We just went through the stability of these earlier. The green one up here is mono-substituted. Look at the double bond. See, it's got 3 on the double bond itself. There's 3 hydrogens and only 1 substituent. This one has got 2 hydrogens and 2 substituents. It's a di-substituted. Di-substituted is more stable than mono-substituted. This is our major product. And that's all we care about. So in your next exam, I ask for the major product. You don't have to give me the other one. If you give me both, I want you to tell me which one is major. Now I happen to have the numbers on this one. We get 81%, show you how major it is, we get 81% of the disubstituted, and we get 19% of the monosubstituted. So you can see how major that one is. And you can also understand now in the lab why we don't always get 100%. Sometimes 80% is great. Sometimes 70% is great. Students always want to think that if I don't get 100%, I failed. No. Sometimes that's as good as you can get is, here, this is the best you can get, it's 81%. Okay. So, we want to form the more stable alkene. Zaits Rule, I'm out of time here. I'll write up his rule next time and we'll do another example. But you don't need his rule. Just know that you're always going to form the more substituted alkene, the more stable alkene. There is an exception to that, and we'll talk about that next time as well. So I will post this video. If you need to re-watch it, I'll post it on YouTube. And definitely for the ones that's trying to Zoom today that couldn't.